sure.
Yeah, please go ahead.
I meet the design specification word by word. I follow the best methods, known methods in terms of design for all PVT conditions. I add extra margins to make sure that I will get the non-good die since I cannot really test on the package for the final test. Everything will be on the die level testing, and I added all the test mechanism to make sure it can be non-good die. Then I pass all the functional check at the die level. Then I publish the full data sheet for everyone to use and also to enable them to do integrations. So with that in mind, that will be my question is, how can I ensure that it will work with the system with other chiplets I bought from the chiplet store? So either I sell it or I buy it, how can I ensure that it will work? And the problem is, we don't see the micro bumps itself. We cannot really test the micro bumps. And what if the device that I buy or I sell has issues? So on the right-hand side, you'll see is a picture that integration in the final MCP or multi-chips package in which I assemble individual die together to create a system on the package. Next, please. So my idea is, and I have a typo here, what we need is some standard deviations. And the first one is we need available to standardize the I/O models. IBIS is one of the I/O standards that widely used, and we could use it as a standard so that we allow the designer to validate their design within the system. But having the I/O model only is not good enough. We need a way to standardize the package, the die-to-die routing model for the timing validations. So every designer has a data sheet, and in the data sheet, he or she will say, my chiplets can support 1 millimeters routings or 2 millimeter routing or 10 millimeter routing per specific data rates. And available, the standardized package will allow the designer to do a systems validation to make sure that the timing is correct. Finally, we need a device compliance certification for assurance. Just like we go out and buy the chiplet and anything from the store. If you buy equipment, it has a UL as a stamp on it. And if I buy anything with a stamp on it, it's certified, then I have assurance that it will work. So the idea will be the designer will bring in the bare die to a certified locations to be assembled with the MCP chiplets for testing. And once the tests have been done, that chiplet will get the AIB design certifications, and therefore he can put it in the chiplet store or a vendor so everybody can buy it. The entire idea is to enable the customers to buy the chiplets or integrate the chiplets with the confidence. And
great. It's about time here, Tim. Thanks very much. Anybody have any questions here for Tim? What's the idea for certification in the chiplet store?
So here, maybe not a question, but first of all, I think that I would agree with everything that is said here, and standardization is very important. I would like to reflect to the comment of that we cannot check the microbumps, and to remind that we actually recommend that visibility from within the chip, electrical visibility from within the chip is a way to check the microbumps with Vector solution, but I'm not saying it's the only one. But I think that this is something that is definitely doable, and we've proven that.
With on-die instrumentation, you mean?
With on-die instrumentation,
Yes.
correct.
But the questions is not for statics checking or performance. It's basically how your device with the microbumps can drive a certain distance. If you do on-die instruments, you don't see the loading on the package level and the others chiplet level. So it's a path towards towards the end, but it's not a complete solution, in my opinion.
So Tim, are you looking for, let's say, for testing perspective compliance? Do you look for something like a loop back from one end to far end and loop it back and get everything passing? Is that something, or?
So if they bring in the bad eye, it could be that the bad eye will work with a known good die. It's a certified known good die. So if we go back to the PCIe, there's a PCIe compliant house. After we're done with the PCIe design, we bring the board with the PCIe chiplets and do the interop with that known device and the system. If it passed, then it's certified. The AIB will do the same things. It's not going to look back by itself, but it will be interop with a very known good device. And that good known device will have the on-die instrument to check for the margins of the incoming signal from the chiplet under test.
So Tim, if you get this on this MCP template, you can do characterization. You can say, hey, look, the design is valid, but you can't do individual die test like for production.
That's correct. And if we do the templates on the MCP substrate, for the AIB cannot really drive the package board. So the only thing that it can drive is the next chiplet with a specific loading per AIB specifications.
So again, I don't want to take too much time because it's not the subject, but I would, again, if you are interested, I would be happy to maybe set some time if you and show you that we believe that we do have also a way to test each individual packaged unit in the production line.
That would be interesting. Thank you.
Okay. Anything else for Tim here? All right. Thank you very much. Next up, we have Mark Beal. Welcome, Mark.
Hello. Thank you for having me.
Please go ahead.
I'm coming through okay, right?
Yes.
Okay. Yeah, next slide. Well, I'm Mark Beal, CTO at Intrinsics. I think that Dave covered that. 5 minutes is pretty short, so let's get into it. So I'm interested in, and Intrinsics is interested in AIB on low-cost substrates. Typically, I'd think of that as an organic substrate, the kind of thing you'd make a package out of, system package. We think there's a lot of opportunity for taking advantage of the fan-out packaging ecosystems and other things here for AIB on low-cost substrates. So obviously, Intel's thought of this. There's the AIB -O standard, which is great. And so the first thing I'll just talk about is some places where we're seeing some enablement possibilities that, if they came forward, would make things easier to use that standard. And before I go any further, I just want to say some of what I'm going to talk about is kind of inspired from what I thought was some brilliant work on the base jump project from Michael Taylor at who's now at University of Washington. And basically they had if you use a standardized pad ring, they had a standardized package, you could actually place orders and buy these things. So they kind of set up this whole simple prototyping ecosystem and supply chain and IP. And that's the kind of thing I think we could do here for AIB-O. So example test benches and test cases I think would be useful here. There's claims that you know, the AIB O has the same inward-facing interfaces as the standard AIB 1.2 or 2.0, but in reality, we know that you only have half the signal, so somehow you're going to have to do channel bonding or other things to get the same number of interfaces if you want to hook up to the AXI adapters. So just showing how that all goes together, I think would be a nice set of examples. Also, I'm not really clear on how the interoperability piece works here, so I think an example there would be helpful. You know, again, there's been in presentations some illustrations of interoperability between the AIB-0 and the 2.0, but then there's talk about link control and so on. So some of that, you know, and to be fair, we have not investigated in huge detail here, but it's not immediately apparent how the interoperability to us works there. So some examples could be helpful there, and maybe even some RTL if there's some adapter work that has to happen to bond two channels and make it look like a single AIB 2.0 pair of channels. We've been thinking about how the DFT works. There's a lot of DFT infrastructure in the AIB PHY IP, but only using half the bumps or tying bumps together. What does that do for DFT? Some examples on how DFT is to be thought of on AIB-0 to me would be also interesting and helpful. The next set of topics really relates to what I said a minute ago about the base jump project that, and I can send a link to Dave if he wants to include it in the presentation later. But
Sure.
you know, in the same way that there's an MCP kind of thing where if the right arrangements are made with Intel, you can get your chiplet kind of validated and mounted into a system, and you can talk to an FPGA and do testing. It'd be great if there was something like that on a organic substrate and still with an FPGA on it. So, you know, there's challenges with how, you know, you get a Stratix or an Agilex, you know, onto a organic substrate that you could then mount individual, you know, AIB-0 pitch devices on, which I'll talk about in a minute. But that would be extremely useful, I think, if there was something like that where we could connect AIB-0 implementations to an FPGA on a substrate. I think Tim actually had this same one on his, which is, you know, substrate artwork and channel model. Like if you were willing to adopt a very specific, you know, set of patterns and artwork, then you would get a pre-characterized channel on a given material. I take this inspiration from what the DDR, if you buy an applications processor and you have to connect DDR to it, you can download like the actual layout of the actual connection between the DDR PHY and the DDR. So, you know, those kinds of things help people deal with these signal integrity problems. And some kind of manufacturing flow that says, hey, we've set up, if you want to order a substrate from this one partner, they know how to do this and how to get it assembled, and we've proven it out. That's something the Base Jump team did, which was you know, kind of inspirational, I think, that you could kind of do this low hassle way of getting prototypes built onto a SIP. So, you know, that's something I think we could look at. And then even though it's a limited I/O, I still think AXI over AIB is still really important. And so clarifying how that works over AIB-0, I think would be helpful. So just quickly moving on, I don't think that
Mark, wrap it up, please. Okay.
Okay. Yep. The only other thing I'll say is that there are very fine line substrates. So I don't think that I think AIB 2.0 on organic is also very important, and I think there's opportunities to investigate that as well.
Great. Thanks a lot, Mark. So any comments or questions for Mark? Yeah, one of the things, Mark, I'll say is that you've got on the link control. You know, we know that the C4 bumps, you can't afford to have all these sideband bumps to use for shift registers for exchanging calibration and control data here. Do you have any ideas? I mean, we thought you'd have to concentrate all the control for all the channels through some sort of sideband like SPI or something like that. You have any thoughts about how to do the link control?
I mean, I don't have any specific thoughts about how to do link control. I see that it's well thought through in the specs that I see there. So I'm not necessarily suggesting that we add to that. But it looked like that was more AIB to AIBO to AIBO. And so this topic is really, if we wanted to make a prototype module that has an FPGA on it and somehow we work out the physical aspects of how to get it mounted, do we have actual interoperability against an AIB spec with an existing Agilex or given this AIB link control question?
Okay. Yeah, that's a little bit of a challenge. That has
That's the challenge I'm pointing out. Yeah.
Okay. All right, folks.
Thank you.
Thanks, Mark. Anybody have anything else for him? Okay. Thanks very much. Let us move on. Next up, Kakong Chan. Kakong.
All right. Good morning, everyone. Let me do a quick introduction of myself. I'm Kakong. I work on the one of the pioneer design on the AIB 1.0. So today mainly to look at from a circuit design point of view, what can make things integrate chiplet easier. So Dave, next slide, please. All right. So I'll look at the from power perspective, power and ground pinout template. I'm looking at one of these ideas. A lot of improvement have been done over the years. When we have this spec, AIB open source spec, I think that's a very good work done on in terms of the guidelines on the signals for the low density, medium density, high density pattern. Good work indeed. I think one thing maybe probably we can further improve is on defining a standard power ground pattern. If you look at the diagram that I have on the right, I just put it as illustrative. It's not exactly the one that was the best, but just to convey the concept. All right. So for example, we should define a standard repeatable power ground pinout patterns for each for low density, medium density, or high density. I say we need one for each because of each one of them have different current demand, things like that. So I believe that if we can make one repeat for all, that's best. But if we need a unique one for each of the pattern, I think we should do that as well. And why I think this is one of the enabler, because of the when we do the design, basically we'll look at how the power get bring into die. And there will be some kind of, in terms of the current capacity, how much current the microbump can carry, things like that. It's not linear. How the distribution look like. One, we have from all the good design experience that we have, and we can define one which we think that will be the best. Then what next will happen is that will enable a universal power network design for a specific packaging technology. For a certain footprint. For example, if we are using EMIB, right, it has a certain characteristics where you can wear the best to bring the power in, versus some other packaging technology, you have a TSV, you can bring the power in. So one thing I want to summarize is that if we have this power and ground template, the pinout, then that could have a standardized power plane design for EMIB. Let's say take EMIB for example, and then what's the best the current can be bring in, and that will become a standardized power design. Once we have that, we can have a good, easy power RLC instructions. Then we can have power models that all the chiplet developer can use. I think this is very much similar like what Tim had mentioned in his presentation, is that there is a standardized die-to-die routing model. So this is, instead of a signal routing models, in this one, I basically emphasize on the power aspect. So this will go hand in hand with the standard channel modeling. So this is the channel modeling will address the SI, and this one will help us to address the power integrity piece of it.
Great. Thanks, Kakong.
Yeah.
Any questions for Kakong? Okay, so I have one. Kakong, I think you're pointing out that our AIB spec specifies where the signals are. And then it has a comment that says that you can insert power and grounds within this array, and still you have to preserve the relative signal locations.
Correct.
Now, isn't your demand for power and ground going to depend on your packaging technology? You know, if you use EMIB versus RDL, some RDL technology, you might need a different power and ground supply.
So yeah, so in that case is that it depends. Like for example, I think the main difference will be on the technology is that whether there's a DSP. For example, EMIB does not have DSP, and other technology may have DSP. That will change how the I guess it's from the on-die power grid perspective that will not change, but what it will enable is that for different technology they will have to do their packaging power grid design. They at least have one common power grid pattern that they can refer to. And then this will enable them to know that okay, where the power will need to route it in. And for example, EMIB that will have they will design the same power plant design, and that can be continue to be reused for whoever the chiplet that will use the EMIB design. Then the same thing happened for the let's say take the interposer, their DSP. They also refer to this standard power grid design, and then they define a standard power grid design for that interposer technology, and that can be reused for everyone, whoever the chiplet that use that packaging technology. So ideally we have one, but the packaging technology may have a slightly different design where create two different power grid model. But I guess it's that the power grid power ground template, the pinout template will remain the same regardless which packaging technology that the chiplet vendor is using.
You know, one approach I've seen is go very conservative. It's like you have a row of power, 2 rows of signals, and a ground, 2 rows of signal and power. And so you kind of solve the problem by overkill. What do you think of that?
I think that we have to take we cannot be too conservative. Otherwise otherwise is that will be not a good, the utilization of the bump will become very low. It's not effective. So I think we have to try to balance over there.
Yeah, Kok Hong, you are touching a very hot topic at the time we defined the AIB spec, and this is one of the topics that we at that times we decided to leave it out to a customer with recommendations, designer with recommendations. The idea was AIB only divide the die to die in terms of the signal. For the power, each chiplet they can use different technologies, and it can be 0.8 or up to 2 volt power supplies, and each AIB can have various power consumptions because it's not part of the specifications. A recommendation is less than 1 picojoule per bit, but for the old technologies, it may consume more power. So it makes total sense to have a divide of power and grounds, and it's still an open topic for us to close it. Yeah.
It's not it's not an easy problem. It's definitely very challenging.
Yeah.
Okay, any other comments, questions for Kok Hong here? All right, Kok Hong, thank you very much. Good topic. Okay. Next up, Bruce Knepper. Welcome, Bruce. Would you kindly introduce yourself?
Certainly. Can you hear me?
Yes.
Okay, great. Hi, everybody. My name is Bruce Knepper. I'm a senior ASIC architect here at Northrop Grumman. And I'm going to talk to you about what we did on our High 3 program with the chiplet design. You can go to the next page, please. So what the High 3 program was trying to do was take some DSP logic targeted towards our electronic warfare designs and port it from what used to be an FPGA design into this chiplet design. The intention here was to be able to nestle this between an Intel A tile and a Stratix 10 FPGA to get some pre-processing in front of the main processing that's in the Stratix 10 FPGA to greatly reduce the power and cost of this function in a system. What we found is that the porting of the logic to the chiplet design to actually do the DSP work was very straightforward and a relatively simple physical design. What we struggled the most with is actually the interface on either side of that to the A tile and to the Stratix 10 FPGA through the AIB. And where we struggled the most is actually the design and the verification of those interface components. If we can go to the next slide, please. What we found is the AIB focused a lot on physical and electrical layers, but the higher levels of that interface stack were less well defined and took a lot of time for our engineers to decipher and design to. If we could standardize those better and pick some standardizations that help enable designers to more kind of plug and play, drop interfaces in, and more easily be able to design and hook up to them, that would be a big advantage from a design and verification perspective. We've seen this all over industry with a lot of standard interfaces out there, AXI streams, and even some of the more recent cache coherent interfaces like CXL, having the components necessary to really enable a quicker time to market for designing chips by having standard definitions, standard interface constructs like IP exact, standard verification models for both simulation and virtual prototyping like emulation, cadence, palladiums, and stuff like that. So having these kind of more drag and drop interfaces to communicate over AIB with higher level protocols would really ease that integration with the chiplet design. And it also reduces risks. Plenty of people earlier have talked about the kind of the risk of, hey, how do I know my chiplet's going to talk to somebody else's chiplet? Having these higher level protocols and standard interfaces would also greatly reduce that risk and ease that integration capability. And kind of mimicking a lot of what also has already been said on this, standardizing those modeling approaches for both interfaces, but also mechanical, thermal, electrical, and everything like that, to give an easier adoption by a user program would be a great benefit. And last but certainly not least, I just wanted to share, because we got a great email either earlier today or late last night, that we just got this ASIC in our lab and powered it up and turned on. We were able to talk to it yesterday. So that's great timing for this phone call. We were very excited to have this chip in our lab and start integration with it.
Fantastic, fantastic. So folks,
all I really had.
What do you think? Any comments about Bruce's concept here?
I think Bruce already we already addressed Bruce in the current AIB 2.0 with the AXI protocol eventually be part of AIB support. So Bruce, I'm in the High 3 and work directly with the NGC on the DSP chiplets. What you say in terms of termination system integrations validation is true, and we share with the NGC about the proprietary protocol, but the common standardized protocol is a good way to go.
Okay. Hey Bruce, this is Dave. So Was the clocking architecture of all the different channels and the sources of the clocks, was that an issue, or was it really, the fact that you're dealing with this raw PHY interface?
I think it was. I mean, I wasn't. So maybe Nishant can speak up if he knows the answer to that. I wasn't directly involved with the details of everything, but it was more the. I think we understood the pinouts and the clocking and the kind of lower level electrical layers, but it was more the. Okay, I know how to get bits from one side to the other, but what do those bits really mean when the other side is receiving them? How is it interpreting them? So I think it was more the data layer than it was the electrical and timing layer.
Okay. What Tim was referring to is we had a presentation from a person in our department, Nij Doraj, a few weeks ago about AXI protocols on top of AIB, and we're working on a design that uses this, both AXI Stream, AXI 4, the memory map version. It's still, you have to do a process of channel assignment. You have to say, hey, my bus is this wide. I need to use 7 AIB channels for my streaming interface, and I want to use a bunch of individual single channel wide memory interfaces. Were you thinking of something that's more structured than that, than just a free form up to the user to make these assignments?
Something more structured, but even going beyond that to say, like the IP exact stuff goes even further to describe, okay, once we've defined an interface, now here's also like all the control registers on the other side. They are, at this address, they have this meaning and stuff like that, such that they can easily be consumed into verification models and stuff like that. So it's even higher levels than that.
Got it. Okay.
Just for your information, all the bits are available to the NGC teams to consume. So description is there and very detailed. I think the questions you probably want is to have a standardized interface on top, protocol on top of AIB. So when you
Right.
You migrate from one interface to another interface, the NGC DSP design can easily port over.
Right. Yeah, you want to make that agnostic of everything inside design. So porting over would be easier if you could just swap an interface, if it contained all the protocol and everything like that. That would also be a benefit, absolutely.
Yes.
Well, fantastic, Bruce. It's a super interesting topic because we received other feedback in this program about how higher level protocols are needed. Because as you know, we provided just the raw PHY interface. So that's definitely an area of extreme interest to me personally.
And it's always a balancing game. There's going to be a lot of people who are going to want to squeeze every single bit of performance out of an interface, so they don't want many restrictions of a higher level protocol because they want to optimize it to what they're doing. But if we're looking at a sea of people creating chiplets out there and they all have to talk to each other, you can't really have enough standardization.
Great. Thanks very much, Bruce. Any last chance? Okay,
Nope.
Thanks.
Thank you for the opportunity.
All right. Next up is Connor O'Keefe. Connor, would you introduce yourself, please?
Hi, everyone. It's Connor O'Keefe from Intel Programmable Solutions Group. Here, what I'm proposing is maybe to actually have a programmable channel direction configuration to improve PHY level flexibility. Maybe if you go on to the next slide, Dave, please. Yeah, so obviously we know our background with AIB 1.0. It's got 20-bit wide DDR buses, 24 channels in each direction, giving us a total aggregate bandwidth in each direction of 960 gigabits per second. Now, we've constrained a lot of things, such as that there's a purely symmetrical bandwidth, so there's equal bandwidth in both directions. And we've also mandated that the TX and RX channels are interspersed throughout the 8mm shorefront. So based on that, why would we consider changing it? I guess we're looking at a lot of use cases as well, maybe beyond SERDES and ADCs, and even some of the AXI ones that have just been looked at, where we're looking at an asymmetry in bandwidth requirements. Let's say if we had a data converter case where we had all ADCs or all DACs, then we'd basically have all traffic in one direction, for example. The other one is that because we're actually mandated to use the full 8 millimeters of shorefront, it means that if we were to look at, and we wanted the full bandwidth, it means that we have to have a die size that's actually constrained to that 8 millimeters die area as well. Whereas if, for example, if we had an asymmetry case where we needed the full bandwidth, but we could get away with a smaller die potentially if we could allocate maybe all the channels to be in one direction only. And the other one that kind of pops up sometimes as well is if we have one high bandwidth channel that's going across the interface, it's managing the skew from, for example, from the top of the physically the top of the AIB bus to the bottom side, where there's actually an 8 millimeter balancing act that has to be done, and we have to do some of those de-skewing algorithms at a higher level. If you could constrain the physical distance, it would simplify that somehow. And the other one is that because we are going over such a wide physical area, if that could be constrained, you could actually minimize on the data bus or clock routing on each of the chiplets at each side of the interface. So that's where that comes from. Now, at the moment, each microbump is defined as being bidirectional, but we don't actually use it in that way. And we're mandating an equal number of channels to be RX and TX at any chiplet interface. And it really doesn't have to be that way either. What I'm proposing here is that the I/O direction could be configurable on a per channel basis, and that would mean that let's say the 1.9 terabit total bandwidth available in both directions is actually configurable on a per chiplet basis. So that's the kind of concept behind this. The downsides to it is that some legacy devices will not be able to exploit this change going forward, and there is a need for the devices that want to be interoperable with lots of chiplets, that they need to have a change in the adapter layer to support such a change. So the next slide, Dave, please. I've just given a couple of examples just using data converters, and on A is what we basically have currently, where we've interspersed TX and RX channels. So obviously, if in this case, if all the ADCs were at the top side of the interface, or top side of the chiplet, then obviously the data reaching those ADCs would have to do an 8 millimeter on die path to get to the other side of the interface to utilize the full shore width of the interface. But if you go to what's being proposed here, you could have something like in B, where you have all the receive channels on the top and all the transmit ones on the lower side. And that allows you to even go to maybe half AIB implementations as in C, where you use just one. You wouldn't in the current guise, if you wanted to use the full bandwidth, you would have to have a shore front. You would have to have a die size on the left-hand side of that interface that actually was the full 8 millimeters in order to exploit the full AIB bandwidth. And it looks at, and D is just a case where we could look at asymmetry in the bandwidth depending on the use case of the chiplet on the left hand side.
Connor, would you wrap it up, please?
Yeah, I'm kind of finished, I think. So it's no change in the interconnector, the AIB I/O, and it's an adapter layer change primarily, and that's kind of it. As
All right, folks, any questions for Connor?
Connor's the AIB is designed for chiplet ecosystem. So if the interface has a lot of customizations, and then it's only applicable to specific chips system, then it cannot be it cannot work well with the ecosystem. But you touch base on the two things, the AIB I/O. In theory, the AIB spec doesn't require a bi-directional I/O. It can be either input or outputs. The recommendation to have I/O per cell is for testing purpose, but we don't mandate a part of the AIB spec is to have a cell with both a bidirectional
okay,
I/O cell.
they're all
Second,
called I/O. So
yes, but it's not
yeah.
required. Second thing is the spec also allow to have either full TX or full RX versus half TX or half RX. So it's the flexibility is built there. The problem will be if the ADC or DAC design just for all TX and all RX, then it may be hard to find the interop with the others chiplet in the markets. So
I think that's what I'm proposing.
Yeah.
I think that's what I'm proposing is that you actually have maybe an AIB standard change that allows that to become programmable and allows you more options, make it easier to potentially design chips at the expense of maybe a small bit more complexity onto the AIB PHY itself. So there's a trade-off there. I accept that.
You know, this is Dave. I was talking to some of the folks who worked on the original PCI Express specification. In fact, this person claimed he worked on PCI. And PCI is half duplex, like it's shared pins that either are transmitting or receiving. And they made that decision when they went to PCI Express to have a full duplex interface because of interoperability concerns. And so I'm kind of wondering, Connor, what you think about the interoperability challenge of going to a picture that looks like the far right, for example. Yeah, Connor, I was just wondering if you thought that was an issue or could be overcome or what?
I think it's an issue that can be overcome. Yeah, that's my thought process on it. Is that the I/O and the EMIB or the interposer of whatever choice you're using actually doesn't change. So the way things are mostly configured today is that the I/O wouldn't change, the interposer wouldn't change. What does change is the adapter layer on the side that needs to be reconfigurable. In this case, the data converter side would be its configuration is done at design time. It doesn't really change. It doesn't have to be adaptable to every chiplet. The chiplet on the right hand side of all these interfaces would have to be adaptable. So on that particular chiplet, there would need to be a more complex adapter layer to support the full range of channel direction configurations.
Yeah, and that could be a problem in terms of meeting the power constraint and die size constraint.
Yeah, I think it should actually help with power, and it should help with die size as well. To optimize die size.
It will impact on the die size and the power for sure. It's similar to the clock network. Before it need to support only 20 pins, and now it need to support 40 pins. The adapters you mentioned, it has a flexibility to support either 20 data coming from the microbumps or quality data on microbumps. And then, yeah, it will be more complicated.
Okay, last comment. Last comment. Anyone, Connor? Great topic, Connor. Very interesting. Thank you. Okay, next up, we have Andreas Olefson. Andreas, would you introduce yourself, please?
Yeah. So, all right. Can you hear me okay, first of all?
Yes.
All right.
Yes.
Cool. All right. So, I I have a long history in chiplets, and so this is probably a little bit different what I'm going to talk about today. You know, so I managed the chips program at DARPA, so yeah. So maybe just go to the first slide. So the idea here is, you know, whether we can create something like Moses for chiplets. So I found at DARPA and afterwards as well that access to advanced packaging is a huge barrier to innovation. You know, unless you're a very big company that has the resources to invest a lot of engineering manpower and also to work with some of the foundries and packaging vendors who you know, the only really way to make them pay attention is by huge volume, right? So we're talking millions of units or possibly billions of units is what it requires to make them change their factories or even give you access, right? So this would be for the something like a defense application, industrial, medical, academic, where your top volume is going to be 1 million units, right? And so the big OSATs and the big founders will rarely do anything special for you for that, right? And so, so can we stand up a Moses-like MPW for advanced packaging, right? So my inspiration here is, you know, if I look at today things that are done extremely well and that not everybody may be aware of in the last few years, you look at something like JLPCB, which is, you know, really low-cost, turnkey, fire and forget type service out of China for PCB boards and assembly. You know, that's really lowering the bar for what people can do, whether it's academics and hobbyists, right? You lower the price enough that you just don't care if you make a mistake, and that's one way of pushing iteration. The other one is, of course, the 3D printing movement. You take somebody like, you know, Shapeways, where again, fire and forget, right? It's cheap enough and fast enough that you can actually iterate in a tight loop without having to simulate everything, right? So I think that's one of the interesting questions. Emulation and models is great, but engineering time in the US is very, very expensive, and sometimes it makes more sense to run an experiment rather than overanalyzing something. And the last data point is, you know, the work that Google is doing with eFabless and Skywater, where I think they're doing some really cool stuff in automating access for newcomers to chip design. And really, you know, using software practices to streamline that, right? So the idea here is zero touch, right? It's self-service. That's got to be the goal here. And so if you look at even Moses, you know, they were back to 1980s and the first Silicon Revolution and Lambda rules. They gave access to a lot of people. I think today we can actually do a lot better than what they have done in the past through software automation. And so I think that's the key. So if we go to the next slide. So there's a you know, the goal here is to give you know, something really low cost. Like, you know, to start with, let's put the bar at less than $50,000, which is sort of what it would cost to do a flip chip package today if you take in all the engineering time. Of course, we'd like to go lower than that, but let's put it at 50,000, and 12 weeks from PO to delivery. And that, you know, doesn't sound very fast, but I've seen many advanced packaging projects where it can drag out to 6 months or more because everything's a project, right? It's not like you just give it a Gerber file or a GDS2, give it to factory, and they've done it 1,000 times before, and you know, it's whether it's a completely automated process or manual, it goes through. But today, every advanced packaging project that I know of is an engineering project. So, you know, to set something like this up, of course, it's going to take a pretty big effort, right? You have to have somebody who has the machines, right? Because if we're talking about AIB, it's 55 micron copper pillar, you know, and you have to have the silicon interposer or some other packaging technology, right? Somebody has to have the factory to do that, the expertise to do that, and of course the willingness to do that, right? So to start with, at low volume in semiconductor, pretty much nobody makes money, so there has to be a path, a bootstrapping path to get there, right? So if for chiplets to make it really make sense, we have a bootstrapping problem, right? So so the money has to come from somewhere, and if you look at the OSATs today, they're just not running at the margins to make this happen, which is why, you know, folks like the Pentagon Navy with the SHIP program or DARPA with CHIPS have sort of had to bootstrap it by pushing in money. And they put in a lot of money, hundreds of millions of dollars. I think at this point, we're still passing the hat around to see, okay, who can make this, get this over the finishing line? And that's a big barrier. So we'll see who solves that. But this idea of creating a sustainable ecosystem for the high mix, medium to low volume has always been a challenge. And my view is that the only way to make that sustainable is through efficiencies like we have today with 3D printing and some PCB applications. And that becomes a softer question, right? So that is sort of my thoughts on you know, could we have a Moses for chiplets? And I think we do need that to make the ecosystem happen.
Wow, fantastic, fantastic. So, folks, what do you think?
I want to echo his inputs, especially the last bullet. Use a template design, fixed footprints, chiplet size, and we are thinking about that as well. It definitely is a big effort, but once we have templates for the die, templates for the package, then we definitely can and we do it at the volumes from the subject point of view. It will empower the ecosystem significantly.
This is Mark
Yeah,
Beal.
Tim, let me just kind of jump off on that statement about simplifying engineering, right? So bringing in the you know, using Intel's work, right, with Michigan, right, which is public, that I thought that was a great example on lowering the barrier for others to participate in an ecosystem. And I think to really bring that to the next level, you just have to keep optimizing and removing inefficiencies and going even further, right, to the point where it can almost be zero friction or zero effort, right? So I think just continuing across that along that trajectory, I think would be incredible.
Yes, yes.
This is Mark Beal. I have just a question either for Andreas or others. I completely agree with everything being said here. I'm wondering if there's a sense of whether this is going to be more doable on if we get to the fine enough line, you know, organic kind of interposers, substrates, or whether this is really something that can be done on silicon interposers, or is it just wide open question?
Yeah, this is Dave. I think the advanced packaging technology is going to continue to be proprietary and difficult to access unless you're a, you know, hundreds of millions of dollars of business. And organic packaging might be the way that we can get this more broadly and more inexpensively widespread.
Yes, and once the organic package templates take take the mainstream by storm, then advanced package will follow.
And just you know, a thought about the zero friction here, right? The materials and supply line barriers here and obstacles are enormous, right? And that's true for silicon advanced packaging or organics right now, right? Like to say that you can get an organic interposer today that's advanced out of Japan and short lead time as a small customer is just not true, right? And so I think my view is that if you want Moses to happen or something like that to happen, you need to have 100% standardization so you can actually carry inventory of all the materials and then just do a quick turnkey. But that means constraining the choices for the customer a lot, right? And I think Mark brought that up, the base jump platform, right? It's you have to take away choice, right? If you're going to enable something like that.
Yeah, that's always painful because everybody always wants something different. You know, our packaging folks at Intel always, you know, throwing their hands up in the air that, you know, reuse is extremely difficult.
I mean, yeah, that's where people have choice, right? You can either have this, 12-week 50K turn, or you can have nothing at all, right? Like those are kind of your two choices. We can talk about, oh, we want choice and all these things, right? But yeah, but it's not going to happen. So why don't we create something that actually can be built, right?
Yes, it's similar to go out and buy tire for our cars. It has a fixed size. So if we make the substrates available at certain size, maybe we can drive customer towards that direction. Cheaper.
Yeah.
I know we're running a little longer here, but this is such an interesting topic. You know, Andres, one of the problems here is that this is not DARPA hard, okay? So that kind of cuts off an entire avenue of funding in this area.
Yeah, I mean,
any
I mean,
thoughts
there
about
is.
that?
Yeah, I mean, DARPA is a small. I mean, DARPA is like a $3 billion a year type funding source, right? And supposedly there's $50 billion coming in chips investments, right? And so just I'm going to push this to Intel. You know, like you guys have the ability to, I think, get a fair chunk of that, right, and put it to good use.
Okay.
So I know there's definitely talk and interest and even maybe line items around advanced packaging. To me, it all, you know, it's going to be putting it to good use and maybe carving out some projects that serve a more general purpose, right, rather than earmarking them for one need, right? It's a platform approach versus a specific program approach.
Okay.
But
Thanks very much.
50 billion goes a long way, and you know, if it's spent wisely.
All right. Any last comments, questions? All right. Thanks very much, Andreas. Go on to our final speaker here, Abram Dutovsky. Abram, do you want to introduce yourself, please?
Sure, thank you. Yeah, so my name is Abram Dutovsky. I've been at Intel, actually AT2D for about 20 or so years, 23 years, working in test, manufacturing, test stability, and now in test architecture and optics and a bunch of other fun stuff. So yeah, we'll be talking about kind of this disaggregated product. You know, how do we make things easier from a test architecture kind of perspective? All right, so next slide. All right, so a little nod to Staples with their easy button kind of campaign. But yeah, I'm basically calling out 5 to 6 kind of easy buttons that I'm kind of describing here that we can kind of run through in sequence and then fall back for questions. But easy button number 1. So I think there's well, I guess we can all admit there's tons of information out there. You know, there's specifications, there's BKMs, there's conference proceedings, YouTube videos, and whatnot. But from an integrator perspective, an Intel perspective, or any other company that's pulling together chiplets, there's really no one-stop shop to go for information. It's really a do-it-yourself kind of effort, and you know, it's a pretty daunting effort since the number of surfaces are fairly large. So what would be, I think, really useful is you know, whether it's AIB or just in general for chiplets, you know, is there a practitioner handbook portal that, you know, can level set the industry, all of the players that want to participate in the marketplace in a common way to kind of level set them on what are the expectations to be successful kind of moving forward. Right now, that doesn't really exist in any sort of coherent way, and it causes quite a bit of frustration, as well as quite a bit of misses throughout companies that like to participate. Easy button number 2. So, you know, one of the things, you know, we do at work all the time, but I don't see it in the chiplet space, is, I think the industry would really benefit from a product deployment checklist. Effectively, here are the items that you need to either receive or generate yourself as an integrator or a chiplet supplier to be successful. What are the expectations? What are the right handoffs that need to happen? As an example, what sort of BIST engines are you using internally? Are you doing full assembly thermal modeling? Yes or no? And if no, why not? Making sure that you have both covered, the mission mode as well as all of the test modes, which can be very different in terms of power. So these things are easy to miss, easy to forget until very late in the game, when they can be extremely difficult to implement or recover from if you see problems. So having something together as a coherent list would, I think, level set folks and various partners that need to interact. So easy button number 3, I think there's a lot of focus around individual chiplets and designs, but not really on system-centric thinking. We talked a little bit earlier in some of the previous speakers about interoperability. I think that's really key here. From a product integrator like Intel, no chiplet is an island. It has to be designed, manufactured, it has to be assembled, it has to work as a coherent system, not only in mission mode with the customer, but also for manufacturing test and debug as well. So how do we debug a chiplet that's buried deep within a stack? How do we deal with customer returns that are coming back, right? So how do we have the right IP in place? Do we have the right pattern content in place from the chiplet supplier? Do we have the right data sources? So really, the system level thinking has to pervade from time, be pervasive from time zero. And ultimately, all the partners that ultimately need to touch this full assembly need to be gamed out in terms of what is the interaction strategy? Are we feature complete as a full design to enable all of these different partners that will ultimately need to touch this full assembly and make that super explicit to everyone? All right, next slide. Easy button number 4. So the chiplet suppliers and manufacturers need to share standardized sets of collaterals and harmonized formats, right? Things like power maps, performance data, chiplet reliability data, data sheets, errata and reports, including things that may come in post-deployment after discovery. Those things are critically important for any integrator, as well as guaranteeing reliability to our end customers down the road. Things like test pattern content for screening, just simple format of wafer maps that can be contentious. So how do we really wrangle all of these different pieces together so we don't have 1,000 different standards that are out there? So easy button number 5, chiplet to chiplet interfaces. And we talked about, interoperability previously. So, what I see as, one of the big challenges in this space is ambiguity in the current specifications. The specifications are generally very good at defining the plumbing, but they don't really tell you or provide any guidance into how you will actually use them for different test modes. As an example, we've had many misses in the past where, as an example, we may have an IBIST engine on one side running, one certain pseudorandom pattern sequence, and another one on the other side running a different pseudorandom pattern sequence. Obviously, those would be now interoperable and not interoperable, and would be a problem. And that would kill manufacturing ultimately, as well as debug. You can't test that interface at that point. But that's really because maybe that was missing in the spec or not clearly defined as a requirement for you to be successful. So think of the investments, and I think this was mentioned earlier, around the interoperability of PCI Express or USB that we've seen in the past. We must use really the same expectations to harden our chiplet interfaces kind of moving forward. And lastly, easy button number 6, and I think this is maybe should have been number 1 possibly, but I think there's very little talk around security and trust architecture, which really I think needs to underpin all chiplet undertakings. From time zero, we have to be a secure first interface, security first design. It's a very complex topic, but I think there's not a whole lot of consensus throughout the industry right now on this and where to go and how to standardize. The threat surfaces are extremely real and extremely numerous in the chiplet environment. And it's really going to take one high-profile case to really provide a chilling effect on AIB or any other interface that needs to be or wants to be standardized to move forward. So I have a nice cool link here at the very bottom from SemiMepTech that kind of shows you the kind of lay of the land there if you're not familiar already. But I think this is another thing that we collectively need to solve to really make things easier and more, to provide more of a provide for a more vibrant marketplace. Those are the easy buttons. Questions?
Fantastic. All right, folks, got any reactions or questions for Abram?
This is Tim's. I think some easy buttons can be part of the spec, but some easy button it normally don't include in the specifications. We would love to have easy button number 4, for example, in terms of the power and so on. So this is actually every manufacturers and design have different specifications, and just like Intel, we have a data sheet for every component we sell. So each chiplet supplier has to have the data sheet, and once they have a data sheet, they should include all information related to how to bring up the data sheet, the chiplet cell. So it's that's something is a good practice, and I would love to specify in the spec, but it's pretty it's not easy to because we cannot really enforce it.
Yeah, it's almost like we need something, a companion to the spec, right? So maybe it can't go into the spec, but it can be a sort of a companion deployment package that travels along with it in parallel.
Right. That would help the easy button number 5 as well.
Yeah, absolutely.
So, Adam, I've got a question for you.
Yeah.
From a test perspective. So this is a statement and a question, 2-part.
Sure.
So the first statement is, it seems like in the IC world, going to the system, the parts per million failure is probably less than 100 for a high quality product, and then the assembly of the board, right, is pretty easy, right? So the yields there are very, very high. Are we ever going to get there with chiplets? Like, is that where we need to get to, where we have a 99.9% assembly success and 100 parts per minute chiplet quality?
For quality metrics, I mean, we need, from the chiplet point of view, we need basically known good die or known not bad die, effectively, since there's really no such thing as a known good die strategy necessarily. But along with the chiplets, we need the capability, number one, high yield. But in addition to that, we need performance data for those chiplets, how are they performing in the distribution of process in some meaningful metric. We also need from those chiplets a reliability metric of some sort as well, since the full ensemble assembly is really limited by the worst case reliable chiplet that's sitting on your full system. So we need our chiplet suppliers to provide that information as well. For us to be successful, for us to guarantee to our customers that the full system will work, over 5 years or, over a certain temperature and voltage range. Yeah, so we need to go to.
Do you see a fundamental difference from ICs?
In terms of the total number of, or in terms of the yield quality metrics?
Yeah,
We need to do a shift left in terms of our content. We need to ensure the chiplets that are incoming are high quality, not just in terms of structural modes, but even in terms of quasi-functional as well. System. Think of like a system level content at a chiplet level. Is that even possible, or can be made possible through DFT or other methods, kind of moving forward, so that we have really high confidence when we pair that with process information from that chiplet to say, okay, these 5 die, when we put it down on a package, that will not only work together and have the right DFT, but will also be performant to either a frequency target, as an example, or a power target, or some combination of the two. Yeah, and then that's sort of how things differentiate in sort of the test world. We have to really do a more shift left than we ever had to do in the past versus some of the monolithic designs in terms of content and how we decide what chips need to be paired with one another to basically leave no chiplet behind when we actually do the final assemblies. It's a huge analytical challenge.
Okay. Abram, do you think it's possible to get near complete tests done at the wafer test level?
We can get structural tests. The things that we can't test are performant problems at boundaries at the interfaces, right? So once you put it into a composite, ensemble, now you have to deal with thermal crosstalk. You have to deal with, ground plane bounce, right, between neighboring chiplets, which aren't even possible to simulate or emulate at the wafer level or singulated level. It adds a whole nother spectrum of challenges just by putting it together, which basically means that at the end of the test process, we need some full assembly SLT test mandated throughout. I don't think we can get away from that.
I think each manufacturer and designer will provide as they sell the chiplet. It will have to come up with a data sheet that require the power requirements, the RF signal requirements, signal quality, and so on for clocks and RF signal. And the couplings. Then there will be another system designer that build the substrate. So for Intel, we are building our substrate, but then we can hire external vendor to build the substrate that put all the chiplet together, and that particular vendor will have to do the package design investigations and validations before they.
Yeah, but we have to think at a systems level as well, right? So at the end of the day, it has to work as an ensemble. So we have to do the full chip, thermal modeling, power integrity modeling as a full system, which means we need models from each of these chiplet suppliers to put into that overall model before we put it together, for real.
That's correct. Yeah.
Yeah.
Hey, this is Mark Beal. I just want to make a quick comment on item 6. I know that on the security, the Navy ship and Intel, and we have a small role, is working on chiplet-based security questions, and I know Intel and Dave in particular have started presenting some things there. So I assume, Dave, there'll be things people can hear about there. Is that right?
Yes. In fact, that was inspiring me for another working group meeting topic here. Is what are we doing on the ship program with intrinsics on a hardware root of trust at chiplet scale? To at least because one of the issues I'm seeing going through here is how do we get broader awareness of what people in different areas are doing? So that would kind of help that scenario, and then put it to the test of folks. I want to look at this MEPTech video and find out what other folks are doing and critique our approach, because there is a big push from the government to get a supply chain security all the way up from as high up at fabrication as you can go, all the way down to deployment.
Yeah, but the security needs to go beyond just trust of individual chiplets. It comes down also to the data that has to transfer. Supplier one of chiplet may not want, secured, their secured data or, raw data from a DFT perspective to go through another chiplet, as an example. So how do you manage that and kind of secure that sort of end-to-end data path for both mission mode as well as different test modes as well that need to pass through other components?
Yeah, it's a big challenge.
Yeah, absolutely.
Okay, folks, any last comments, questions? All right, fantastic. Well, I think that's it for today. Thanks everyone for joining, and a special thanks to the presenters for providing us your views. And I think it's been a fantastic meeting. I really appreciate all your participation.
Thanks.
Thank you.
Okay, folks, that's
Bye-bye.
it. Thank
Bye-bye.
you. Bye.
Thank you very much. Bye.
Okay, thanks.